Recording. Okay. So, welcome everyone. We are delighted to have you here today. It's a pleasure to host Dr. Laura Donnay from SISSA, whose work on asymptotic symmetry, soft theorems, Carolean physics, and celestial flat space holography has significantly shaped several major directions in the field. In today's seminar, she will first give an overview of flat space holography, followed by a discussion of BMS particles. Laura, thank you for joining us. The floor is yours. Whenever you're ready, you can share your screen and start. Thank you.
Yeah, thanks a lot for the introduction, and thanks again for the invitation. As I said, it's a great initiative that you have taken, and it's a pleasure to participate. So I'm going to try sharing the screen and set up the presentation. Great. All right, so yes, I'm going to talk about flat space holography. And I'm going to review some part of it. Of course, it's not going to be an exhaustive review on this topic. It has been evolving a lot in recent years, so I won't be able to cover everything, but I hope to be able to give you the main features of this program. And then I will turn to some recent work direction, which I believe are a novel direction for flat space holography, which is based on representation theory. And this will be the part related to the so-called BMS particle that I'm going to define later on. So I just want to say that I am very happy to take any question at any time, even what you might think are naive or basic questions. I'm very happy to answer anything. So please don't hesitate to interrupt. Otherwise, it would be a bit. It would be much better if I get question during the presentation, so that I can see a little bit what is clear and what is less clear for you. Okay, so let's start. So the main question, of course, about flat space holography is try to understand to which extent the holographic principle, which has led to very important advances in string theory and quantum gravity, how general this principle is. So recall that according to this principle, quantum gravity is encoded in a different theory, which doesn't involve gravity, that lives in a lower dimensional space-time. And it's very well understood for the case of anti-de Sitter spacetimes with a negative cosmological constant. And there the dual theories is a conformal field theory that lives at the boundary of ADS. However, for the case of a zero cosmological constant, it's far less understood, and in fact it's an ongoing research program. And we still don't understand whether to which extent this holographic principle holds and which form it takes exactly. So why do I care about these kind of spacetimes? Well, I think they are interesting for the following reason: is that they essentially describe a very relevant spacetime. So I'm talking about four-dimensional asymptotically flat spacetime, which can describe physics from collider physics to essentially astrophysics, as long as you stay, of course, below the cosmological scale. Then you might be interested in understanding the effect of a positive cosmological constant, which describes the world we live in. However, up to cosmological scales, this is a very good approximation to work with, the fact that it's asymptotically flat. And why do we think that there is a holographic principle at play? Well, we have this celebrated formula of Bekenstein and Hawking, which is telling us that the entropy of the black hole scales with the event horizon area, so with the boundary, or scaled with the area of the black hole and not with the volume. And this formula is valid for asymptotically flat black holes as well. So it seems to indicate that holography is not a mere curiosity of ADS spacetime, but rather a sort of fundamental feature of quantum gravity. Soon after Maldasena's paper in the late 90s about ADS-CFT, people started to try to generalize or to take the flat space limit of ADS-CFT. So it's in this regard, flat space holography is not new as an idea. Of course, people attempted to do that very early on in the late 90s, but soon it was realized that this was not as easy as taking lambda to 0. And there are many reasons why this program is much harder to address and to formulate in a precise manner. And I would say that the main obstructions or difficulties, and you might consider obstruction or just challenges, is the structure of the boundary of flat spacetime, so which is represented in this Penrose diagram here. And so I recall that in this diagram, you have the notion of the conformal structure of spacetime is preserved while distances are not preserved. And you have this feature that the boundary of flat space involves several pieces. So you have first in blue here, the future and the past null infinity, denoted by this letter scry plus and scry minus, which is the boundary to which massless particle go to. You have a future and the past, and you have this null time, which is going to play an important role here in this talk. So please recall that this u is the null coordinate, is the coordinate running along this direction. This is the boundary relevant to discuss scattering of massless particles, but you have on top of that this what looks like there are points in this conformal compactified spacetime, but it's an artifact of the construction, if you wish. But you have these boundaries here, time like infinities, the future and the past again. Do you see my mouse, by the way, when I move it? Yeah?
Yes.
Okay, cool. So this is the boundary where a massive particle come from in the past and reach to at the end. And on top of that, you have this locus here called spatial infinity, which sort of acts as a junction point between location between the future and past and null infinity. So you have all these different boundaries, and one important fact is that this boundary is not time-like. It's a null or light-like boundary, this one in blue here, which is very different from what happens in ADS spacetime, where you have this nice time-like boundary in ADS. Moreover, if you want to describe realistic scenarios, and in particular, say, gravitational radiation in your setting, then you have to deal with fluxes and gravitational radiation in flat space, which are escaping through infinity. While in ADS-CFT, typically we impose some sort of Dirichlet boundary condition here at the boundary. And in other words, that's why we usually say we put quantum gravity in a box in ADS. But here in flat space, you sort of have to deal with a very different sort of problem here, and I think these two reasons are the main differences compared to the ADS CFT case, and which leads to complications. Now, given that, you might wonder, how should we proceed? How should we proceed to understand flat space holography? And a good starting point is always to follow symmetries. And in particular, this story of symmetries in flat space holography has played a very important role and is going to be at the core of this talk. In fact, in asymptotic flat spacetime, it has been known for some time that there is the phenomenon of symmetry enhancement, essentially due to the presence of radiation. So if you wish, I don't know what your background is, but another example of symmetry enhancement is, for example, in ADS3 CFT2, where this asymptotic symmetry group of ADS3 in space-time dimension is the conformal group in 2 dimensions, which turns out to be infinite dimensional. So here is another example of symmetry enhancement, where the global conformal group get enhanced to an infinite dimensional group, which is the Virasoro group. So if you wish, the symmetries I'm going to discuss in flat space are a similar instance of this symmetry enhancement. And these symmetries are called Bondi-Messner-Sachs or BMS symmetries, which are featured the symmetry enhancement where the 4 usual Poincaré translations that are isometries of flat spacetime get enhanced to an infinite dimensional group, which is called the BMS group. And I'm going to recall the main feature of that. So in other words, the BMS group is the symmetry group of asymptotic flat spacetime. And again, here I'm focusing on 4 space-time dimension, 3 time and 1, 3 space and 1 time. You can discuss what happens in higher D. It's an interesting story, but I'm not going to cover that in this talk. So as I said, this symmetry group was studied by Bondi and collaborators in the long ago, in the 60s, where people at the time, you have to remember that at that time, people were not sure that gravitational radiation existed. They thought that this might be an artifact of Einstein's equation. It was not clear that it was a physical phenomena. So these people really tried to provide a framework to understand gravitational radiation. And in particular, they came up with this definition of an asymptotically flat spacetime, which takes the following form. So essentially, it's just a metric which is looks like Minkowski spacetime plus some 1/r correction. So at large distances, it looks like flat. So this is just the first line here is just Minkowski written in this maybe unusual coordinate system where I'm using this retarded time u. And I'm also using some stereographic coordinates, so complex coordinates z and z bar instead of the usual theta and phi angle. So for instance, so this is Minkowski, and then you see that you have a 1/r expansion here following with a bunch of functions in this expansion. So this, okay, I'm sorry that this MB should be the same M as here. It's a typo. So this M is called the Bondi mass aspect, and NZ is called the angular momentum aspect. And on top of that, you have the presence of this function C here, which is called the gravitational shear. And essentially, the gravitational radiation is encoded into this function here in red. There are many things one could say about this class of spacetime. Here, I decided to write it down in the coordinate, in this Bondi gauge, in the coordinate system, but you can define a notion of asymptotic flatness without resorting to any specific coordinate system. This was, of course, well understood by Penrose and others in the 60s as well. But essentially, you have to imagine that we are living here, or LIGO, your gravitational wave detector, is here at infinity, at null infinity, at future null infinity, and you're measuring some gravitational radiation coming from an isolated system, coming from the center of the spacetime, which is reaching you at scribe class. Let me know if there's any question or comment about this notion of asymptotically flat spacetime. But just roughly speaking, it's just some correction to Minkowski, some 1/r expansion of that. And you have, of course, in this ... you have a bunch of, subleading terms in the expansion, which I'm not going to discuss here. Okay.
I have a question.
Yep.
So we have du as time and dr as the radial coordinate, I guess. And then rest is the spherical part of our choice is somewhat coming with this gravitational radiation. So how can we, this CZZ is the gravitational radiation part, right? Somehow we will find it as the radiation. No, you said, did I understand correctly?
Yeah, so more precisely, the gravitational, what encodes the gravitational radiation is the time derivative of this function. So the retarded time derivative of this function here, which is called news. And this is the time derivative of this CZZ, which encodes the gravitational radiation. So essentially, it's the fact that this quantity here, C, evolves in time, so which captured the flux of radiation. So, for instance, another way to understand this is through this famous it's called the Bondi mass loss formula. So Bondi derived an equation. So on top of this expansion, you have to impose Einstein's equation. And Einstein's equation gives you some constraint on how this function here in blue evolve in time. So they tell you what is the du, the derivative respect to u of this function m here, for instance. And when you work this out, the formula is telling you that the derivative in time of m, so the evolution of this mass aspect, is equal to minus essentially the square of the time derivative of that. So the flux essentially is just telling you that if you have an isolated system of Bondi mass m, the mass decreases in time, and how much it decreases is given by the flux of gravitational radiation escaping through Scri plus. And this flux of radiation is directly related to the time derivative of this quantity here. So it makes sense. It's just you have a system, it emits gravitational wave, and so its Bondi mass decreases in time. And it was this formula that was very important to understand the nature of gravitational radiation. And yeah, does that answer your question?
Yes.
Yeah.
One follow-up though. So we said that the time derivative of the mass somehow will give something proportional to the CZZ, and it will just about the losing of mass and radiation. So will it look like some kind of a Stefan Boltzmann law for black holes, like radiated mass with time-dependent mass somehow gives some power radiated power or something like that? The change in the mass, will it obey that kind of a law, or is just something new about this this thing?
So yeah, I mean it's I would say it's a different. I mean, then you can wonder. You're asking about the thermodynamic. How does this?
Yeah.
How would this relate to the thermodynamic? Yeah, I mean that's. Yeah, I think that would still be an extra layer to put in the game, that to understand exactly there.
Okay.
Yeah.
I had a quick. Are you going to be telling us more about where this metric comes from, or is that clear?
No, I'm not because for reason of time, but
Okay.
essentially, yeah, it's I can try to answer in some ways. Okay, you what this metric is, okay, there is a choice of coordinate. Of course, there's a choice of coordinate system. There is a choice of gauge here. For instance, you see there is no the r squared term, for instance. But essentially, yes, it was this sort of expansion came out after an understanding of what are the kind of expansion you might want to have here. And especially you might wonder why you have this precise fall-off condition, why you have these powers of R here, what they are dictated. So it's a long story of how people came out with this fall-off condition. Essentially, it boils down to work of other people in the GR literature. Yeah.
Right. No, that would be a
Yeah.
long story. But I mean,
Yeah.
to summarize, this metric basically describes any asymptotically flat spacetime with arbitrary gravitational radiation. Is that the idea?
Yeah,
Or
that's
is
the
it
idea.
only
Yeah, that the idea is that it describe an isolated system which is emitting a gravitational radiation, and this gravitational radiation is incorporated here in this red piece. So the red this red piece also to come back to the previous
but
question.
is there any requirement of spherical symmetry on the system, or is it
No,
is
no,
no?
no.
Oh, okay. All right. Thanks.
Yeah. Okay, is there any other question? Good. Yeah, very good. So it's indeed the whole topic on itself to discuss this definition. But let's take this as our working framework and ask. Okay, what this guy ask is they looked at what are the symmetries that preserve this expansion, and what they found is what is famously now called the so-called BMS super translations. So just to make clear what we are doing here. So you might be familiar with the notion of a killing vector, right? It's an exact symmetry of the spacetime. Here we are playing a slightly different game. We are asking about what are the symmetries which don't leave this metric exactly unchanged, but just the only requirement is that it preserve this kind of 1 over R expansion. It preserve this fall-off condition here, this boundary condition. But what you're allowed to do is you're allowed to change this function here, M, N, and so on. Okay, so that's the concept of asymptotic symmetries. It's not a killing symmetries. You're allowed to change the function here in the expansion, but what you are not allowed to do is to mess up with the powers of R in this expansion. Okay, you have to preserve the asymptotic form. And when you look for these symmetries, so at the level of infinitesimal killing vector field psi, you find on top of the usual Lorentz transformation, which are written in this coordinate system like that. So big A denotes the angles, Z and Z bar, or theta phi, as you wish. So it's a two-dimensional, it's two coordinates here. On top of the Lorentz transformation, you find what is called super translation. So it's called a super translation because instead of having just a function, a constant, a shift by a constant, now you are free to shift your coordinates by any function. So t is any function on the angle, on the celestial sphere, if you wish. Okay, so it's an infinite dimensional enhancement because you have an infinite amount of ways of changing the coordinate, of shifting the coordinates. You're allowed to do any change you wish by this, because this function t is arbitrary. Okay, so it's, instead of having 4 translation, you have a whole functions worth of super translations, and then you can work out the algebra of these vector fields, and what you find is the following commutators. So essentially, the main feature of that is that the 2 super translations commute. So it's an abelian ideal of this group. You have, this is just the usual Lorentz commutation relations, and the last equation is telling you how what is the commutator between super translation and the Lorentz transformation. And what you find is that this super translation function here has a transform with definite weights under Lorentz or conformal, global conformal transformation, if you wish. So, and here I take advantage to define a sort of notation I'm going to use later on. So I'm going to, for me, I'm going to call a super translation, well, it's just a notation of, it's just a definition of what is your convention to count weights. You know, there are different conventions, CFT convention, conformal geometry convention. I mean, there are different conventions you can use. To me, I'm going to denote then as this curly E here, which denotes densities of weight 1 on the celestial sphere. So in fact, it's related to the minus the sum of this. Sometimes in CFT, people call H and H bar the conformal weights. Here, this one is minus 1/2 minus 1/2, and then I take a global minus sign of that. So anyway, it's just a notation. So at the end of the day, what is the BMS group in 4D is the semi-direct, here the level algebra, semi-direct sum of Lorentz with these weight 1 densities on the celestial sphere. Okay?
Question?
Yeah.
So this Z and Z bar, these are coordinates, stereographic coordinates on the celestial sphere, right?
Yes.
Okay, and so basically the super translation is just telling you to how you can move along the null light rays as any function of which is defined only on the celestial sphere.
Mm-hmm. That's
Okay,
right.
just to clarify that, and the Poincare algebra is sits inside the BMS algebra.
Yes, I'm going to re-emphasize
Okay.
this. A very good point. Yes, the Poincare group is a subgroup of the BMS group. It sits inside, but not in a unique way. I will come back to that. But essentially, if you take the 4 lowest harmonics of super translation, you get the 4 usual Poincare translations. So it's really, it sits inside. But in a non-unique way, I'm going to review that. Thanks. Very good. Thanks a lot for the questions. I'm going slow, I guess, but I guess it's better anyway. I can skip some stuff if, in case we are. How much time? I understood that there was no strict limit, but I don't want to keep you for hours neither.
We have no time limit.
No
As
time
soon as we
limit.
want to go, we okay with it. We want to learn, so no problem.
Okay. Yeah. So then it's very good. We go slowly, and then I stop a lot to ask questions, because otherwise it doesn't make any sense. Okay, very good. So that's this BMS group. So just historical note, I mean, this BMS group was found by this guy in the GR, general relativity literature, and then it stays there, no one cared, for 50 years, essentially, apart from a few people. they were originally disregarded by the author themselves, Bondi and others. They really thought that it didn't make any sense that they didn't recover the Poincaré group as an asymptotic symmetry group. They really wanted to see the Poincaré group, and they were really annoyed by this super translation story. So the author themselves were a bit annoyed by this fact and didn't understand what was the physics so much of this enhancement. And then Strominger came by in 2013 and realized that these symmetries have implications for the S matrix. In other words, in this seminal paper called on BMS invariance of gravitational scattering, Strominger realized that it's also a sort of story that could be detailed in much greater detail, but that essentially this symmetry constrains the gravitational S matrix. So as soon as you have a scattering process taking place in flat space, so here I'm depicting some incoming massless and massive particle, they interact somewhere in the bulk and they exist. This symmetry constrain these scattering amplitudes. And to do that, you have to sort of understand how the BMS symmetry that act in the future relate to the one acting in the past. And this was the new ingredient that Strominger added to the story, and that was key in understanding that the symmetry constrained in a global way the global structure of flat spacetime. Okay. So these symmetries are actually telling us very important lessons. Moreover, they have associated gravitational wave observable effects. They are the so-called memory effects. This is also a very interesting story. So people are hoping to measure these effects in the future gravitational wave experiments, like at the Einstein telescope or LISA. And moreover, the super translation enhancement was not the end of the story. There is, in fact, further symmetry enhancement that, on top of the super translation, that can arise, including the fact that the Lorentz group can also be enhanced to include the full local, so the full, the Virasoro group acting on the celestial sphere. And these 3 points are the things that in the, I guess 10 years or so, 10 years ago, really was a new input and new insights for the program of flat space holography and both the so-called Carolean and celestial holography. Well, indeed, this in celestial holography, there is this question in general in flat space holography of where do you expect or do you want to formulate your boundary theory. So there are two natural proposals, so to say. One would be to look to, well, this is the idea behind celestial holography, is to propose or to look for a dual theory of quantum gravity in 4 dimensions in terms of a 2-dimensional theory living on the celestial sphere, so the sphere at infinity. And that's the proposal put forward by celestial holography. Or you could try to have a different approach and look for a theory which is codimension 1, which lives on the null boundary of flat space, so on Scry. So now it's a 3D null hypersurface. And also you should include the time-like infinity as well. This should be also included to have a full holographic setup. And this was called Carolean holography. I know that you have had some previous talk on this topic, so I guess some of you are familiar with Carolean physics. So really, Carolean field theory is the same as saying I want a BMS invariant field theory because the conformal Carroll group in D dimension is isomorphic to the BMS group in the higher dimensions, so it's really the same. We could have well called people like a lot the word Carroll because it for some historical reasons now it's called Carolian holography, but you might as well call it BMS invariant field theory. It's really equivalent in this set. So essentially, yes.
I just have a small minor historical point.
Yep.
The Carolean this thing geometry was discovered by what's his name? I forget his name. This French physicist, right?
Lévy-Leblond, yes.
Yes, exactly. So, I mean, ideally we should be calling it Lévy-Leblond holography, but I suppose it's too late for that.
Oh, but you know the whole point of Lévy-Leblond was actually to propose this name Carl, and you know, and he's very, and he's, and I think that was the most, I mean, the very nice aspect of his work was actually to provide this name, and he also you know, like we invited him in some Carl meeting, and he's very happy about the fact that this work of him where it was at the level of the group, right? It was looking really at the contraction of the Poincare group, and he called it the Carl group. So I mean, if you wish, I mean, there are many. I mean, I think he was this contribution of giving this name was very, very fun and very smart of him, and but you might want to call him Lévy-Leblond if you wish, or But I mean, also I should say that a lot of stuff in this business about Carroll holography and the geometry of null physics, we should give a lot of credit as well to Penrose and collaborators, because really these guys basically understood everything about what we now call Caroline geometry, and it's been revisited in the last year. But if you dig into these old papers, everything was already written. Yeah. Very good. Any other questions or comment about that? If not, I'm going to present. So okay, I don't know how I'm going. I see it's already 45 minutes. I'm talking about. I'm just going to give you a review of some aspects of celestial holography. Well, by the way, you can see this quote from that I took from the book of Roger Penrose. I hope I'm not going to take so much time, but again, please, doesn't mean that you shouldn't ask questions. So let me okay, here I'm just giving you some review in case you're interested in learning more about that. Of course, I'm very biased because I'm following essentially my own perspective on this thing, but there are other reviews, there are very nice reviews in out there on arXiv. So if you're interested, please have a look at that. So as I said, what is celestial holography about? It's about the statement of that the symmetric is encoded in a two-dimensional celestial conformal theory. By celestial, we mean that it lives on the celestial sphere, and it's also a convenient way of calling this yet to be understood theory, because we don't know for the moment to which extent it's 2D CFT as we are used to. And the idea behind that is pretty simple. I have to hide this panel. Okay. Is essentially use conformal properties as much as possible and make them manifest. So one way to make, well, you know, you have a scattering in flat space. So you have global, I mean, you have in conformal invariance from the Lorentz invariance. So by definition, it's built in, but usually it's not manifest because you work with plane wave packets where time translation is more manifest rather than the Lorentz transformation are more manifest. But the idea of celestial holography is, okay, let's try to see, to make manifest this, sorry, I have this panel that is bothering me. How do I present this to hide? Okay. And how do you do that? Well, instead of working with the usual plane wave packets, you perform this integral transform. It's called a Mellin transform. And essentially what it does for you is that it trades the energy omega of your particle, can be, here I'm focusing on massless particle, for a new parameter called delta. And delta will play the role of the conformal dimension of your, what is now called a conformal primary wave function. In fact, you can check exactly that when you recast your plane wave packets into this basis, thanks to this integral, you can check now that the object you get transform manifestly as a primary field, like in a 2D CFT, of conformal weight delta, or that you sometimes denote as the sum of the left and right weights, h and h bar in a usual CFT. So it's just a fact. It's just recasting your the Lorentz transformations in a very manifest way. It's very simple idea, and so what you do is that what you can do is, if you apply this Mellin transform on all your particles involved in this scattering. So if you have a scattering amplitude, this curly A denotes the scattering amplitudes involving n massless particle, you do as many Mellin transform as you have of particle, and through this Mellin transform, you will have an object on the right-hand side, which will transform nicely under conformal transformations. So it will be labeled by n conformal dimension delta. And then you want to see, you want to interpret this as some correlation function of a two-dimensional celestial CFT. And you can try to infer, when you have this idea in mind, you can try to see what are the properties of this theory, okay? So just by starting, you know the amplitude, take your favorite amplitude, let's say maximally elicitive violating gluon amplitudes. You do this Mellin transform, you get something, and then you interpret it as a correlation function of a 2D CFT, and then you read off what are the properties of this theory. So it's, if you wish, it's really bottom up, and this defines for you the theory. Of course, it's just the first step in this holographic program, but it's an important one. You can do a similar thing for massive particle. I'm not displaying the formula here, but it also applies. And then you can also explore some features of these amplitudes. So for instance, you can see that when you have, it's just a kinematic fact that if you take two of your momenta to be parallel, so if you take the collinear limit of your 4-dimensional amplitude, this will amount to take Z1 and Z2 very close to each other. So it allows you to describe operator product expansion in the celestial CFT, and people have been looking at that a lot. There is also this feature that because you integrate over all energies, here there is a UV-IR mixing phenomenon happening in the celestial CFTs, which plague typically these celestial correlators. They suffer from divergences typically, and they are also have distribution, distributional nature. However, there are different strategies that are being taken in the field. Again, I refer you to reviews for if you're interested. You can look at celestial amplitude string theory, thermal background field. There are many strategies that interesting thing you can study. The thing I want to focus on here is what is the universal behavior of this this putative celestial theory, and this universal behavior is in one-to-one with the symmetries that I discussed a bit before. In particular, the symmetries, the asymptotic symmetries, the BMS symmetry I discussed in their extension, provide an important input for celestial CFT, namely, it provides currents, like currents you have in 2D CFT for the theory. And this is closely related to this story about soft factorization of amplitudes. So it's a well-known fact from Weinberg in the 60s that quantum field theory, which involve n particles plus an extra particle, can be a photon, can be a gluon, can be a graviton, whose energy is taken to 0, factorizes, and you have these factorization formula for in the limit where omega goes to 0, you have a leading, it's called a leading soft theorem, and you have also a subleading soft theorem. And the soft physics of celestial CFT is governed by these asymptotic symmetries. So just to give some example of that, you have the leading soft theorem worked out by Weinberg. Here I'm focusing on gravity, but similar stuff hold for gauge theories. The soft theorem is nothing but the word identity associated to these super translation symmetries. And here, this is the way that super translation act on this function we discussed in the beginning, this gravitational shear. They shift they shift the shear by this function f, which was, sorry about that, it was called t in the beginning. It's a super translation parameter. And these symmetries provide a 2D current for celestial CFT. So this is it's called the super translation current. Yeah, it has given weights on the celestial sphere. It's a primary of delta equal to 1. And it has the following OPE with the operator on the celestial sphere. So, okay, there are many things could be said about that, but the main point I want to make is that this symmetry, this asymptotic symmetry, in particular super translation, provide a current for celestial CFT, and the OPE of any operator in the celestial CFT with this P is constrained to take this form. So any candidate for a 2D celestial CFT should satisfy this OPE relation, for instance. So this is strong constraint for the theory. And notably, you have also a very rich story related to this further extension of symmetries, which are sometimes called super rotations. They are just the same as Virasoro symmetries. These ones are related to the subleading factorization of Weinberg, but it was not found by Weinberg, it was found by Cachasso-Strominger in this case. But they relate to the subleading soft graviton theorem, and the current associated to this symmetry is very important for celestial holography because it provides a stress tensor, so a primary, a 2,0 primary, which turns out to be the shadow of a delta equal anyway. And these objects can be obtained from the bulk. So from this news function that I was talking about, this time derivative of the shear, there is a precise expression of this T here in terms of the bulk quantity. And this current obeys the word identity of Virasoro, I mean, like in of a usual stress tensor in a usual 2D CFT. So this was really important realization for celestial CFT, the fact that you had these extra further symmetries that provide a current. So is there any question about that? Probably it's a bit fast if it's the first time you see this, but feel free to let me know. So the main message here is that asymptotic symmetry gives powerful constraint for celestial CFT in terms of OPA relation associated to current. Okay. And there is a long story. There is a much richer story. It's called W infinity symmetries that I'm not going to discuss. But just to let you know, this is just the first set of a much richer story. So I think I'm going to close here the sort of short review about celestial holography. And the main question, there are many open questions in this program. The main question is essentially, can we define in an intrinsic way what is this theory? I mean, we have a lot of input from scattering amplitude recast in this basis, but we still don't have a full understanding of what exactly this theory is, what are the axioms of this theory, to which extent it resembles to the CFT. These are very important open questions in this program. Okay, is there any question on this business?
I have I guess a
Yeah.
misconception. So
Yeah.
for the figure that you given here, so we have this flat space written in this coordinates so that we have scribe plus and future null infinities and everything, and we somehow equate this to celestial sphere. But as I understand it, for every point on scribe plus, there is a sphere, right? So these are the spheres in there, or it's another object that is equal to that one?
Yeah. So indeed, this is something that might often be confusing, but you really have to think that there is only one celestial sphere in the future, okay, and one in the past. Even though it looks like at each cut, at each constant u, you have a sphere. All these spheres can be canonically identified to each other. So you really have to keep in mind that this celestial, there is only one celestial sphere in the future and one in the past, and then there is the relation between the two is through this matching condition at I0, but it's not like you have an infinite, like all these spheres at different cuts can be canonically identified. So yeah, there is, at the end of the day, there is, if you identify the celestial sphere in the future, in the past, through these matching condition that have been studied in the literature, there is only one celestial sphere at the end of the day. There is only one celestial sphere. That's the idea. Yeah, and that's a good point.
Thank you.
Yeah. I have a question. Can we take a very short break? Like maybe 1 minute? Yes, is it okay? Yeah, I'll be right back. I am back. Thanks. for the break. So is there, do you guys have any other questions or comments about that before I go on? I hope not to take too much of your time for the last part, but again, I prefer that we are on the same page and we discuss rather than me talking on myself.
Yeah.
Okay.
Excuse me, can I ask a
Yes.
question?
Yes.
Yeah, so are the collinear divergences somehow worked around in the kinematic singularities language, like without putting any cutoffs?
So, can you repeat the question? Sorry.
The collinear divergences in the
Yeah.
language of celestial sphere, are they solved without putting any angle cutoffs?
Are they solved? What do you mean by solved?
I mean, like not getting divergences.
Oh, no, not that I know. So yeah, that's an interesting question. Is how indeed these collinear divergences are imprinted in and into the celestial operators. I think people have been looking at that a bit, and indeed, I'm going to talk about very closely related things about the reason why we have infrared and also collinear divergences. So yeah, in the later of the talk, because the question is indeed how to properly deal with these divergences, and can we provide a framework where these divergences do not appear. That is going to be I know a strong motivation for what I'm going to talk next. Yeah. There any other question or comments? Okay, if not, I'm going to transition to the last part of the talk, where you see sometimes this program has been a lot of progress. However, it's not always clear what are the rules of the game when it comes about understanding this theory, what kind of axioms and so on. So sometimes my impression is that we are lacking a rigid framework, and what I want to argue today is that representation theory surprisingly has not been used a lot in this program, but it provides a very solid and rigid framework for any attempt of flat space holography, be it Carolean or celestial. And this brings me to this part about BMS particles. So this is based on this work with Xavier Beckart and Yannick Herfray from France in Tours. So let me again maybe motivate why I'm going to talk about representation theory in the context of holography. Well, if we recall, in ADS-CFT, symmetries play a fundamental role, and in fact, fields in ADS, so bulk field and CFT operators, realize the same representations of the conformal algebra. Is really a step zero of holography, if you wish, that they organize according to the same representations. What about flat space holography? So an analogous statement for flat space holography should read as the operator in celestial CFT or Carolean theory should be organized according to the unitary irreducible representations of the boundary symmetry group, which, as I explained in the beginning, is the BMS group. And these representation, unitary and irreducible, I'm going to follow the name of proposed in this paper and call this a BMS particle, because this is exactly what, well, a Poincaré particle is a unitary representation of the Poincaré group. Here we have an analogous definition for the BMS group. And yeah, so surprisingly, these representations have not been studied a lot in the context of flat space holography until recently. And I also want to, it's also important to address the following question, is that what kind of Hilbert space are we claiming that we are trying to map in this? If there is such a thing as flat space holography, it should be a statement about also mapping Hilbert spaces. And this question is very complicated in flat space holography for the following reason, is the fact that essentially all your scattering amplitudes are plagued with infrared divergences. So you have a bunch of infinities that probably you have encountered in your quantum field theory course a lot. Especially in any loop computation, you will encounter these infrared divergences. And so infrared divergences, let's recall why they arise. They arise as a penalty of a penalty that you're paying because you're doing something, you're assuming something which is not correct. Well, everyone does. That is the framework of textbook, but it's the fact that the asymptotics, you're identifying the asymptotic states of the interacting theory with the states of the free theory. And if you have long-range interactions, this is something that is not okay to do. And essentially, that's the reason why infrared divergences appear. However, the reason, let me also say that while we as physicists can still live, can still wake up every day and still be physicists, the reason why infrared divergences, the problem of infrared divergences is not as serious as what I might sound, is the reason is because people show that in cross section, so that it's for the so-called inclusive cross section, so these divergences cancel in observable, so in the cross section. So this is why people are concerned. They are not concerned so much about infrared divergences, because the so-called inclusive cross sections, these infrared divergences cancel. However, it's still a problem in my opinion, because it just essentially we are lacking of a solid framework for quantum field theory if we don't tackle this, and essentially we cannot define properly the S matrix because of these infrared divergences. Let me just mention that in QED, of course, this problem is very old, and it was already argued in classical papers by Chung, Kibble, and others, that because of this feature, you need to the usual Hilbert space of usual Fock representation is not enough, and you need to depart from this usual Hilbert space. And in fact, this story is tightly connected to asymptotic symmetries, and it was nicely revisited in these papers. So here I'm going to talk about gravity in most of what I'm going to say, but everything I say is also valid for QED. It's a very, very analogous story. So sometimes I'm mixing insights and references from QED and gravity, because to me they are really qualitatively the same. Is the understanding that infrared divergences arise for usual conventional quantum field theory states, the textbook quantum field theory state, as a necessity to respect BMS conservation laws. And this, of course, brings us back to the fact that the scattering matrix is BMS invariant, and if one wants to respect, if a scattering amplitude wants to respect BMS conservation laws, it will be translated for conventional states as it will be it will imply infrared divergences in the scattering process of conventions. I hope I'm going to make this point much clearer in the following. But essentially, what all these things are strongly suggesting that we took very seriously is the fact that the states, a proper state of S matrix, should not merely be the usual conventional Poincare particles, but should rather be BMS states or their QED analogs. Okay. So I hope the motivation is somehow clear. So this question really addresses this issue of infrared divergences, and is really, if you wish, taking very seriously this statement that this matrix is BMS invariant. So okay, and we know that the usual Fock representation is not enough, and we know that we have BMS symmetry. So why shouldn't we study BMS particles then? Seems an obvious thing to do. Is there any question about the motivation? I hope to make some of the aspects about the BMS conservation laws clear, but essentially that's what we had in mind behind this idea.
Are you going to tell us? Are you going to tell us more about the BMS particles and that representation?
Yeah. That's yes. I'm going to explain that. Yes. Very good. So I already showed you this. So just a reminder of what is the BMS. So I'm going to look for a representation of this group. So just a reminder of what this group. So this group is the Lorentz with the sum and direct sum of these super translations. And recall that there are weight 1 densities on the celestial sphere. This was the weights that we could read from this last line of this algebra. And as I was asked before, yes, the Poincare group sits inside the BMS group. So this is just the Poincare group in 4 dimensions. It's a subgroup of the BMS4 group. But the inclusion is not unique. Namely, there are infinitely many ways of putting the Poincare group inside the BMS group. There are all these. You can choose. In other words, I give you you can choose a Poincare group inside BMS. I can choose a different Poincare group. All these choices are valid, and there are an infinite amount of these choices. This is related to the fact that super translations are infinite dimensional, of course. And the choice of a Poincare group inside BMS was called by Ashtekar choice of gravity vacuum. This is just a terminology which is used a lot. So choice of gravity vacuum just means a choice of Poincare inside BMS. There is not a unique way to pick this group. There is an infinite amount of doing so. This is just a fact about these groups. However, it's an important remark. Of course, all this is well known, but I'm just rephrasing this for a purpose of representation theory later on. There is a canonical inclusion of translations into super translations. So this is also something that I mentioned earlier on. So if you have a translation T mu, so it's just a finite, you have 4 translations, you can include them in a canonic way into super translation. So these are super translations, this curly T here. And the way this inclusion is realized is through using this vector here, Q mu. So Q mu is a vector that pops up everywhere in celestial holography, for instance. It's a null vector, Q mu, and I'm going to use it a lot. So it, in particular, it realizes this inclusion. So this is maybe a fancy way of saying the fact that I already mentioned is that everyone agrees that the 4 translations, there is no ambiguity of that. It's the 4 translations are just the lowest 4 lowest spherical harmonics of super translation. This is all what this statement is saying. Okay, so it's an important remark. And now, let me, before I give you what is the BMS particle, I need to introduce a final thing, which is the super momentum operator, p hat. I'm going to put hats explicitly on operators for reason you're going to see next. So what is this? Well, it's essentially the generator of super translation. Okay, you have the here T is the parameter of the symmetry transformation, which has this weight -1/2 or it's a weight 1 density on the sphere sphere. This guy has weight conformal weight 3/2. This is just it has to be like that. And the BMS algebra can also be rewritten like that. So it's, if you wish, this is just to recognize the Lorentz algebra, and then this generator of super translations. So this super momentum, the super momenta commute with each other. Okay, and they transform as primaries of weight 3/2 under the Lorentz group. Okay, so it's an object. This is the generator of the symmetry that is going to play an important role in the next slides. So now I can finally turn to the construction of BMS particles. So to do that, I'm going to parallel everything with the usual notion of Poincare particles, so what we call usually a particle. So let's review this briefly for Poincare. So Poincare, I'm going to study unitary reducible representation of this group. So it's just R4 with the Lorentz part. So I'm following here Weinberg. It's really the derivation you can find, for instance, this. So the first step is to define a momentum as a dual of translations. So P mu lives in the dual of translation. And you have a notion of pairing. This is called a pairing between the translation and the momenta, which is just the contraction with the index mu in this case. And then you fix an orbit of the Lorentz group. So in practice, what you do, you take a reference momentum and you act on it with the Lorentz group. And this defines for you what is called the little groups. Okay, little L here, and the orbit. So the orbit is the quotient of the Lorentz group by the little group. And you can classify what are all the possible stabilizer or little groups for the Poincare group. And you get this list, just these 4 groups, okay? SU2, ISO2, SL2R, and you have the trivial one. And this defines for you the orbit or the mass shell, okay? So the mass shell for massless particle is the light cone here in green. The mass shell for massive particle is this hyperbola, okay, over here. Why is this so? Because again, is the quotient of the Lorentz group by SU2, so it defines for you a hyperbola. And you have also the tachyonic mass shell, which I'm not going to discuss so much, but this is exactly what you do. And finally, what is a Poincare particle is a wave function with the support on a given orbit of the Lorentz group, and this really gives you a unitary irreducible representation of the Poincare group. Okay, so of course, as physicists, I mean, this is somehow maybe of course, now we know, it would be, we know what is the momentum of a particle. So this derivation might seem too abstract for what it is, but it's really necessary to keep this in mind if we want to do the analog story for the BMS group, which is a much harder problem because it's an infinite dimensional group. And there we have less physics intuitions to start with. So the idea is just now that we are going to do exactly the same for the BMS group. So for the BMS group, we have a much harder problem, so to say, because now we have these infinite dimensional super translations, which are these weight one densities on the celestial sphere. But let's proceed in the exact same way and define the super momenta, the object I commented on before, as the dual of super translation. So it will be a weight densities of weight -3 on the celestial sphere. We called this weight before -3 half, well, 3 half, 3 half. This is weight -3 on the celestial sphere. And we have a similar notion, well, analogous notion of pairing between super momenta and super translation, given by this integral over the celestial sphere. And now you do the same and you fix an orbit of the Lorentz group. So now you take a super momentum reference and you act on it with the Lorentz group. And the task now is to classify, like Wigner did. Wigner did for us the classification of the little group for Poincaré. Now you have to do the same and classify all BMS little groups. And luckily for us, these mathematicians and physicists as well, have done the classification of BMS little group. Especially, you see, the key player in this business was McCarthy in the 70s, who in a very long series of papers aimed at understanding BMS representations. There are many things that could say. I mean, this literature is not as clear as it could be, so to speak. But if you work hard enough and spend enough time reading those papers, like my collaborators did, you essentially extract, at the end of the day, the following result. Is that McCarthy is telling you that at the end of the day, there are 11 possible little groups. Okay, not that bad. And moreover, because you just take a quotient of the Lorentz group by these little groups, the mass shell are also finite dimensional. So they are the mass, now the BMS shell will be dimension, instead of being dimension 3, like the mass shell of Poincaré, they can be dimension, okay, 0 is the trivial thing, or up to 6. And just to give you an idea of what this is a table I try to write to clarify. So here are the Poincaré little group for massless and massive momenta and their associated orbit. Now for BMS, you have a bigger variety of possible little group. For instance, you have on top of ISO2, you have R2 and R or U1. And as a result, the orbit, because it's the quotient of SO3-mon by this little group, is a sort of higher dimensional generalization of the usual Poincaré shell. Okay, so you really have to think of this BMS shell as higher dimensional generalization. Well, they're really you have to think of the Poincaré shell, and then with the say for instance a U1 fiber on top of this shell. So it's a higher dimensional. Yeah, it's a bigger it's a bigger shell if you wish. But the key aspect of all this is that we know all the little groups, and now what is a BMS particle is a wave function with support on a given low orbit of the Lorentz group, where you have these different choices and different little groups. So this is essentially the idea behind, well, the construction of BMS irreducible representation. And of course, the hardest part of all this is to understand the physics behind this representation, because we have many more representation to deal with, and extract the physics is something that was not done in this long series of paper I showed before, and that took us some time to understand what is the physics of these new representations. Is there any question on this business? I hope I'm not going. I will try to finish in a reasonable amount of time. But okay, let's go back to it. So as I said, yeah, I mean, these works also raise a lot of physics question. What, you know, it's, as a physicist, just imagine I would tell you as a physicist what a particle is. I would tell you, okay, I would tell you, well, here you are, I classify for you all the little groups of Poincaré, and that's it. No, this is not enough, right, for physics. It's not enough to have the classification of the little groups. You also want to construct explicitly a wave function and work with these wave functions, right? That's all the thing that was not done and was not understood in the literature, and this is what we try to address. Essentially, what do BMS state look like? Okay, so I'm going to give you a hint of what these particles are. But to do so, I'm going first to focus on a subset of those representations, which are the so-called hard BMS unitary irreducible representation, or hard particles. These ones are very special and very privileged because, remember, Poincaré group sits inside BMS, and these hard representations are the ones which are in one-to-one with the usual Poincaré particles. And I'm going to demonstrate this in a way that is really quantum field theory textbook, and which I hope is helpful. So I'm going to start. So I'm going to show you that any particle you know and love from quantum field theory, here I'm going to focus on a scalar field, carries a representation of BMS, but a special one, the hard one. So let's start with the scalar field. And let me briefly review what happened to be very, very concrete, how to get a realization of Poincaré. So you have these Poincaré generators, right? It's the usual stuff in any quantum field theory textbook, which provide for you a realization of the Poincaré algebra, because they close this they close the Poincaré algebra. Okay, that is the usual realization of Poincaré on creation, for creation annihilation operators. Now I'm going to do exactly the same, but to show you that there is a BMS representation hidden there that can be uplifted for free through this key formula, is the fact that to any momentum, for a massive or massless particle, as I can associate it, what I'm going to call the hard, because I'm focusing on this hard stuff now, a hard supermomentum, P, which takes the following form. So if you have if it's a massless particle, P squared is 0, and the hard momentum will be a distribution. It will be a delta function of z minus zeta. Zeta is the angles. It parameterizes your momentum. And if it's a massive momentum, well, this is the hard supermomentum. I mean, there is a reason why this expression take the form they have, but essentially this is representation theory is giving you this expression, or giving you these expressions. So if you give me a momentum, I can associate it to it a hard momentum via this expression. Okay. Notice that this hard supermomentum depends on the momentum, right? But in a non-linear way. It's going to be important. You know, you have this cube here. Here also it's non-linear. It's more hidden, the fact that it depends on the momentum through this zeta here. but it depends on the momentum in a nonlinear way.
What is
Yes?
zeta?
Yeah. So okay. So here they are two different coordinates, right? They are the z and z bar, and zeta bar are the. So for any massless particle, I can parameterize my null momentum by 3 variables: the energy and zeta bar, the points on which it's pointing toward the sphere. But I need to distinguish this zeta from the zz bar here, which are I'm integrating over. But yeah, that's the. Is it clear? Yeah.
Not quite.
Okay.
I'm trying to figure out what. So, I mean, these are both coordinates on the celestial sphere, right? The zeta bar and the zz bar.
Yeah.
And and so if momentum, if for a null momentum, right? You're defining the momentum using the usual prescription, right? And then you're saying that this capital P is what?
Yeah.
What is this capital P? What do you call it again? It's the
Yeah, I
generator.
call this. I'm going to call this the hard supermomentum, because
Right, hard supermomentum, right?
Yeah. So it's later on I will have, before I presented the supermomentum in the generic way. Now since I'm focusing on this specific hard representation, I'm just showing you the form of this momentum for this hard representation. That's why I call it hard supermomentum. And this is just an identity. So you see.
Yeah. So if you integrate it, you just get that.
Yeah, this one is obvious, right? The fact that if you have a massless momentum, which is equal to omega q mu zz bar, that this equation holds is trivial.
Okay.
It's less obvious that for a massive particle this also holds as an identity, but it's true.
So this expression is basically so that you can put both of those cases together in one.
Yeah, exactly. So for the massless case, this identity is, but this object is key. So I really need to introduce this object, P of zz bar. Yeah.
Oh, okay. Thanks.
Yeah. So I'm just giving you what is the hard supermomentum. Again, the reason why these functions are what they are is there's a reason, but okay. So now I'm going to do recall. You had this before. You had this Poincare generator. This Poincare generator is just the Lorentz invariant measure, B dagger B, with the momentum. Okay. Now let me promote this to a super hard super translation generator, P hat, where now instead of putting P mu, I'm just putting this infinite dimensional generalization of hard supermomentum. Okay, it's just a slight modification. Well, it's an uplift, if you wish, of the usual translation generator to a super translation generator. And now what you can check, this is the magic of representation theory, is that, and of this expression, is that these close this algebra. So this P hat, so this generators, this hard super momentum generator, close this algebra with the Lorentz. And this is nothing but the BMS algebra that I showed before. So in particular, these guys have these famous 3 half weights here. They commute with each other. Yeah, so essentially this is the bracket of BMS. So the upshot of all this is the following. Each Poincare particle can be lifted through this map to a hard BMS unitary irreducible representation. You can see it, but this is a realization of the BMS unitary irreducible representations. So that's for free. So what this computation shows, and again, it was sort of written in some place through an asymptotic expansion, but here you see it doesn't really need any asymptotic expansion or anything. It's just the fact that if you have a Poincare representation, you can uplift it for free to a BMS representation. And so you have a one-to-one correspondence between this subset of BMS representation are called hard. Okay, so that's the crucial, I think, very overlooked fact about BMS representations. So unless there are any questions about these hard representations, I'm going to proceed.
So this construction of this operator was first shown by you, this super momentum operator, the hat capital P. Yes, this.
Yeah. Yes, written in this way. However, right. I should say that in the literature about BMS and other, so you see, these expressions have appeared. I mean, for instance, for the massive case, I'm thinking about the work of Campilli and Lada. Campilli and Lada have understood what is the asymptotic expansion of a field when you approach time like infinity, and such expression arise. The people sometimes refer to it as the bulk to boundary propagator and so on and so forth. So I'm not saying that this is, pieces of these have appeared in the literature, but I think what is new here is just to repackage this in a very conceptually clean framework, which are representation theory. But of course, we have extensively used previous literature and previous results.
No, of course,
yeah.
Of course. That's always the case. Yes.
Yeah, exactly. And let me say that this story about hard representation, it was understood by Sachs in the 60s. That but he just focused about the massless ones, that they could be that Poincare could be lifted to BMS representations. And for the massive case, the important paper was by Longhi and Materazzi. But they proceed in a very different way. But essentially, the fact that BMS representation, the hard representation, were in one-to-one with the Poincare, was around in the literature. Okay, I'm not claiming that we are the first one to make this statement. However, it's the presentation and the conceptual framework I think is much cleaner in this way. And also here I tried, so this is a new presentation that I'm working on right now, and it has the advantage of you see, I didn't have to tell you how you expand the field near time like infinity or anything like Campilli and Lada did very nicely. So it also captures the two cases, masses and masses, at the same time. So it's the most economic way, at least, that I can talk about that.
Okay.
Yeah.
So the particles we described in here, so they are also endure in the scattering process or any other loop calculations or anything. We also still have this UV IR mixing, right? So is this somehow makes this problematic, or anything that is coming from that UV IR mixing divergences that we have some problems in it? So how it enter the picture, in the sense that we both have UV divergences and corresponding IR divergences, and then I don't know. I just curious about how it enters the picture, or any way that we understand in that.
Yeah. So. I mean, the UVIR, just to clarify, just to make sure, the UVIR mixing I was talking previously was really in the context of celestial holography, when you do this Mellin transform, right? When you transform these wave packets into this Mellin transform. Here, I'm not exactly doing working in this setup for now. but anyway, yeah, I mean, the things could be said about how celestial representation for celestial holography will be, of course, extremely close. This is going to be very relevant for a representation of celestial operators and so on. I'm not going to discuss that so much, but that, yes, I will come up with I will try to explain a little bit how these representations are relevant, at least for understanding infrared, the infrared divergences. So the main message I want to promote is don't scatter usual Poincare particles because you will have divergence. Just scatter BMS states instead, and it's yet to be proven. So this is still a new, this is still very recent, our understanding of this representation. We don't have so far a as S matrix built on BMS representation. This is a program that I actively want to pursue in the future, but it's not like we have understood everything. From now on, we are really at the first steps of understanding what is a one particle BMS representation, and then how to scatter these generic representations. It's a complicated problem. We are working on that because it's a challenging task. But yeah, it was just a disclaimer about the fact that I don't understand everything so far about scattering of these generic representations. Yeah.
Thank you.
Okay, good. So message, your usual Poincare particle, you can uplift them to the BMS representation, but they are only just what I call the hard one. This is not all, right? We have infinitely more representation which are calling for some interpretation, and we have to do that. So the business, most of the a key feature that we wanted, that allowed us to understand the physics of BMS particle, is amounted precisely to understand to which extent the generic representation depart from the usual Poincare particles, right? And in other words, we wanted to understand what extra infrared degrees of freedom, if you mean of soft physics or memories, you name it, what are these extra degrees of freedom as compared to the Poincare particles? And to do that, we had to understand in the mathematical ways of understanding of this question amounted to understand the decomposition of a generic supermomentum into what we called, to make contact with the literature on soft theorems and so on, soft part and the hard part. So the hard part is it was the straight P that I just showed you before. Okay, it's just the same as the one that I talked about previously. And on top of this hard part, you have another piece, which we call soft, which, if you wish, encodes these extra infrared degrees of freedom, which are supposedly, normally should be very relevant to discuss infrared divergences. And the soft part involves 4 derivatives, for some conformal reasons, of this curly n. And the curly n is just the weight 1 densities on the celestial sphere. It's also called sometimes the memory mode in this literature. But what I want to emphasize is not, okay, the existence of such an object was understood in celestial holography, but the key thing I want to point out is that there is a decomposition which is unique, Lorentz invariant. However, it's nonlinear, of a generic supermomentum. So remember, it's the dual of supertranslation, which is the building block in the BMS particle, into a soft and a hard piece. Okay, and this is really the observation that allowed us to discuss what is the new physics, what is the new infrared degrees of freedom compared to just the Poincare particles we know and love. And one way to understand what happens if you, let me ask the following question. Suppose you take a scattering particle of your usual, you take a scattering process of Poincare particles, the usual setup. And now, with the thing I told you before, you think of them as BMS particles, the hard ones. And you scatter them. So the key thing is that these hard particles are not enough because momentum conservation does not imply conservation of this hard, what I call the hard supermomentum. And so in other words, if you have a scattering of Poincare particles, it will not imply conservation of supermomentum. And this is why this is the case. It's just because if you recall, the hard piece is this expression here, and it's non-linear in the momentum. So conservation of momentum does not imply conservation of hard supermomentum. And this is the reason, the deep reason why Poincare representation are not enough to conserve BMS symmetries, or if you wish, to conserve the supermomentum. So the point we want to make is that it's not enough to look at this hard part only, and one is forced to look at the generic representation, which include both of these pieces, the hard and the soft, which of course is in line with what Strominger have been telling us for many years. Okay. So main lesson, hard particles hard representation are not enough in general. Conservation of supermomentum needs also a soft piece. And now I'm just going to finish. Wow, it's been already a long time I'm big talking. So I think it's the last slide, so bear with me. I'm just going to outline what is the BMS wave function. So just really mimicking, now we have the concept of supermomentum. We can talk about BMS wave function. So this is the formal way of writing a BMS wave function, but thanks to this hard and soft split, you can write a BMS wave function as the following expression. So well, now you see you have, instead of having states labeled by just your momentum, your states now will also be, this is omega z bar, just to be sure they didn't write the z bar, but your states are also labeled now by this curly n here. So the soft piece. So you have, your particles have extra label, to be expected, right? Because it's a bigger group. And you have to, what is a Poincare wave function? Well, sorry, a BMS wave function. You have to consider wave function with support on the given orbits of the Lorentz group, and the given orbits are given by the different little groups I showed before. And you have this integral that looks a bit scary because it seems a bit a formal integral, but if you're interested, it's not as scary as it looks. You can write this down in a very explicit way. These are just some finite dimensional integrals whose form depend on which little group you are dealing with, but this was worked out in detail in this paper. So essentially, that I think I'm going to stop there, and you can really work out explicitly in different instances what are this is the most generic form of a BMS wave function, but you can take example and play a bit around with this representation to see exactly what is extra in this representation. And moreover, it also gives a sort of a physical interpretation of a BMS particle as some quantum superposition of usual particle over the space of gravity vacuum, which which is also a statement in line with other things in the literature. But please see the paper if you're interested in more detail about that. So I think I'm going to essentially conclude here about technical stuff and maybe give some final comments about where the story is going. Yeah, so in the first part of the talk, I outlined this research program of flat space holography, where quantum gravity in flat space is encoded into a celestial theory living on the celestial sphere, or equivalently as a conformal Carolean field theory. The main message I wanted to convey is that if we really want to have a fully fledged holographic dual theory, as in ADS-CFT, this correspondence between bulk and boundary state should involve a correspondence of representation at the level of representation of the symmetry group, of the boundary symmetry group. Here, in this case, the BMS4 group, and possibly their extensions, but as the very, very first step, we should understand the representation of BMS. And surprisingly, it has not been looked at very extensively in the literature because probably this there are some papers that were not super easy to read. But now we start to understand what are these one particle states, at least very well. And also one of the key message I wanted to convey is that the usual states are in fact can be thought of as BMS representations, specific ones, the hard one. These states cannot by themselves fulfill super momentum conservation, and that's the reason for infrared divergences. And of course, the next question and the program that this thing raises is to attempt for a fully BMS invariant extension of quantum field theory, or a BMS matrix. And this program has, I think, the potential of defining infrared finite scattering matrix elements. So besides flat space holography, it might provide a very nice and novel framework for quantum field theory, which would be free or infrared divergences. So essentially, this program would amount to take a Weinberg volume 1 and essentially redo everything. And each time you see Poincaré particle, you replace this with the BMS particles and see where it goes. But to our view, this will necessarily require the notion of BMS states. And what is an open question here is to understand S-matrix elements involving these BMS states. We are working on that. And also I should say that all this business carries through for QED, for the asymptotic symmetry group of QED, which has a structure which is different than the BMS group, but almost identical in spirit. And you can run the same stuff. You can construct the BMS, well, the QED, so to say, asymptotic, the representation of the asymptotic symmetry group of QED, and it's probably a very promising direction first to understand the S matrix for these particles, and gravity will probably come at a later stage because, of course, we understand extremely well scattering for QED, so we have a lot of results that we can match on to. So I'm stopping here. Yeah.
Ma'am, actually, a question.
Yeah.
So why are we assuming that we need to have super momentum conservation? Like in our usual QFT, the momentum conservation comes from LSE. LSE shows us that the outgoing and incoming particles are on shell, right? So why should we assume that the whole momentum, the super momentum, should be conserved?
Mm-hmm. No, that's a great question. So, in fact, if you wish, the reason is because we understood now that the infrared divergence problem was a consequence of the fact that the usual quantum field theory state do not respect BMS symmetry. So it's not a, you know, it's not like it's given a priori that you should have, that one should have these conservation laws, but it built on the recent literature understanding explicitly why infrared divergences are forced to appear when you don't respect BMS symmetries. And this was also shown by Strominger that the S matrix has these symmetries, and it's in fact it's so you were mentioning LSD. It's in fact interesting to notice that LSD formula does not apply for massless particles or for theories with as soon as you have long range interaction. It just does not hold. It's just not. It's not new. What I'm saying is very well known, but it's interesting precisely that LSD does not quite work for massless particles. So it's also, if you wish, I think a sign of the same problem. I love the infrared divergence. Yeah, this is, yeah. But of course, I mean, a priori, one might, yeah, it could have been, it could have been otherwise, that but it's just what the amplitudes are telling us. The amplitudes are telling us that, okay, you don't want to impose supermomentum, fine. Then you will have infrared divergence in your face. I mean, as a consequence of that. Now you can say, okay, I don't care that my scattering elements are infrared divergence, because I care about cross sections, and cross section are finite, and this is fine. This is an okay point of view. But if we want to go a little bit further, then I think this framework can be of help. So I'm happy to take any more questions, but I'm going to stop here. And thanks a lot for your patience and for listening.
Thank you. Thank you for this great talk.
Yeah.
Do we have any other questions? I guess not.
Well, so I was looking at one of the references which you cited earlier by McCarthy, because the title caught my attention, and the title is, where is it? Elementary particles and yes, asymptotically flat spacetimes and elementary particles. So it seems that as far long ago as 1972, he had already, so if you look at the abstract, he says that, where is it? He says that elementary particles should be defined as irreducible unitary representations of the group of asymptotically flat spacetimes in general relativity.
Absolutely. Yeah.
So,
no, absolutely. So I think McCarthy was one of the few to really care and be interested at these representations. And I think there is a lot of credit to be given to McCarthy for that. What I should say is missing is the physics behind this these works. So, for instance, you were talking about this reference. This reference is number 3 in this list here, and yes. Just to give you an idea of how tricky understanding the physics of these works is. In this, essentially up to reference 7, McCarthy was using assumptions for on which space is the supermomentum defined. And in the first, in his first papers, I hope I'm going to say this right, but in the first papers, you know, he was working on the he didn't allow the supermomentum to be distributional. Well, if you remember, I showed you before that for the massless case, you have to have a distribution. You have to be distributional. So McCarthy didn't allow for this possibility, and he was using some mathematical assumptions which were physically not good enough. Everything he did is correct, but you know, like you need to understand what kind of functional space you need to be using. And in particular, what he didn't notice, and this is what Girardello and Paravicini pointed out, is that at some McCarthy, these guys were happy because they seemed to exclude the continuous spin representations with their assumption. But what Girardello and Paravicini pointed out is that, look, McCarthy, look at your defining, look at the definition of this, the supermomentum, and he didn't realize that his assumption were excluding also all massless Poincaré representations. So in this in this history of paper, McCarthy didn't realize that he was excluding very important representation, which are the massless usual Poincaré particles. And then that's why he rewrote a series of papers later to correct that and extend and allow for the supermomentum to be distributional. So you see, it was a very convoluted history about understanding the physics of these representations. And again, I think a lot of credit should be given to these references. I think they are largely not read because they are difficult to read. I think if you have to look at one references, it would be this one, the BMS group in the nuclear topology. It's a complicated work to say that he allows for supermomenta, which are distributions. And just to give you another idea of what is even though these works exist, the lore or the common knowledge, if you would ask people who had read this carefully, they would tell you that there is nothing more than the usual Poincaré representation in these works. That the thing that McCarthy did there is essentially there is nothing extra than usual. Then there is no sub-physics, for instance. There is no infrared degrees, extra degrees of freedom, and it's understandable why you might think that when having a look. And this is what took us a lot of effort to actually understand what McCarthy is doing. Also, McCarthy is pointing you in a direction which is not exactly the one you might want to follow, because he has this classification of all little groups. But in general, you might want to look at the case. What it doesn't look at is I think it's the most interesting physical case, the one of generic supermomentum. So McCarthy classifies all different little groups, and you might be tempted to follow him and say, okay, let's take a specific little group and understand the physics of this specific little group. But it's not, I would say it brings you in the wrong direction if you try to go that path. Anyway, long answer to say, yeah, lots of credit for McCarthy. First one to be interested in that. I mean, to be fair, the fact that BMS representation should be looked at, Zach's also mentioned that in the 60s. But the hard part is the physics behind that. Yeah. And again, we don't understand everything about this representation yet, so we need help, and there's a lot of things to be done.
Ma'am, one more thing. So when you say the super momenta should be conserved, you are considering only the massless particles, right? If you consider massive massless scattering, then only the massless particles would come from Scri, that is the null boundary where BMS algebra is there. So generally, when we consider massless scattering, get the problem of this collinear divergence also, right? So will this be solved here with this
Yeah, so just to clarify, so when I mean conservation of supermomentum, I mean for both massive and massive particles. It happens that for massive particles, the supermomentum takes a different form, you see, but this is the hard part of the supermomentum for massive, and this is the one for massless, the distributions. But the statement of supermomentum conservation should hold for both cases.
Okay, but for massive particles, why do we have BMS supermomentum? Because massive particles don't go to the null boundaries. Why should they have BMS symmetries?
Yeah, so it's indeed it's something that I think it's a bit overlooked. You see from these representations here, there is nothing really. The fact that you can uplift this usual Poincare to BMS, there has nothing to do with gravity, really, right? There's nothing to do with gravity. It's you don't even need. In fact, you don't even need an asymptotic expansion. That's why I think that this presentation makes it very clear that it doesn't really require this asymptotic expansion. The statement when gravity will become important is as soon as your particle is going to couple with gravity. And then you see, and it's analogous stuff with QED. As soon as you are going to couple with your photons, then this sub-theorem arise, and you will have this the infrared divergences and so on popping up. So as soon as you don't, you see, like all this story will come as soon as you are going to couple your field with gravity. Otherwise, I mean, this is if you wish, yeah, it's. But does it answer?
Like I partly understood. I still don't clearly understand why mass. Like I know that I understand that we can lift the massive particle this supermomenta, but I don't see why they should have this supermomenta conservation, like massive ones, because they don't even go to null infinity. So, like they should have some other sort of symmetries which are related to say time, like infinity or whatever.
Yeah, but this is really that these hard. Okay, you see, I think it's a bit of misconception that maybe is due to the way that maybe things are phrased sometimes in in some presentation or stuff. But BMS acts everywhere. It acts at scribe plus, at scribe at I plus, at I minus, and at scribe minus as well. It really acts everywhere, and in fact. It's you should not think of it as something that is only relevant for massless particle. It really acts globally, also at I plus. And if you wish, there is a way to understand that as well in terms of Carolean stuff. That you had that we mentioned about there is also a Carolean structure at I plus and I minus. So nothing really is only valid for null infinity. It's really something that, yeah, the BMS symmetry does act at I plus and I minus. And again, also I want to refer also to the work again of Campilli and Lada, and who have early on show that. I hope that clarifies. I understand that it might be confusing this idea of what really does the feature null infinity or massless versus massive particles, but yeah.
Okay, yeah.
Yeah.
I guess we have one, we can say the last question from the chat. If I just fastly read it to you, maybe you can answer it, and if you like, if it's okay for you, if you have time. one last
Yeah.
question. So, are these BMS particle states related to the Fadeev-Kulish dressed states? The question is this.
Very good. Very good. I don't know how much time it's a very interesting story. How much time do you give me to answer this question? Oh, but maybe I have a magic slide for this question that I'm going to show. Yeah, so in the paper we wrote called BMS particles, you can have a look in the supplementary material. We make the explicit comparison with Fadeev-Kulish, because indeed this person is extremely correct to point out this story. So if you don't know about all this story of Fadeev-Kulish dress states, never mind, but this is aimed to answer this question. So essentially, a point of view on that is that Fadeev-Kulish dress states are trying very hard to be BMS, but supermomentum eigenstates, but while sticking to the usual QFT framework in terms of creation annihilation operator. And so if you wish, in the usual conventional setup, Fadeev-Kulish is probably the best thing you can do, even though there are a lot of unsatisfactory aspects about these dress states, especially these ambiguities that arise in the dressing. If some of you are familiar with that, which depending on that you can a priori derive different analytic properties of this matrix, which doesn't seem a very good thing. So to answer in a sort of concise way, BMS particles are momentum eigenstates, and things that are not Fadeev-Kulish are not, or these dress states are not super momentum eigenstates. In fact, they are not even momentum eigenstates. However, yeah, you can try to make an explicit relationship, and I refer to you in the supplemental material of our paper for the explicit expression. You can try to see exactly how these dress states are trying to shoehorning BMS eigenstate into the usual quantum field theory language. So I hope this answer the question. So answer yes, and yet very different. They are different objects, but very nice. Very of course, these Fadeev-Kulish things are. We hope to be able soon to make even more precise statement about that. For QED is also very clear. For the original Fadeev-Kulish is very clear. How this relates to the dress state, or contrast, what I would rather say, how they are also differ from the BMS states. Yeah, thanks for the question.
Okay. Thank you. Thanks again, Laura, for.
Thank you, and thanks a lot for all the questions and comments.
It was a great presentation. Thank you for everything.
Yeah. I hope not too long, but thanks a lot.
No. Yeah.
Okay.
I'm stopping the recording now.